For years, astronomers have carried a quiet suspicion that the early universe was not the simple, quiet, and chaotic place our textbooks describe, but something far more dynamic, structured, and alive with complexity. The prevailing view in cosmology painted those first billion years after the Big Bang as a time of cosmic infancy, where hydrogen and helium gas floated freely, slowly gathering into clouds, gradually condensing into the very first stars. The expectation was that everything back then was primitive, chemically simple, faint, and sluggish in its growth. But suspicions are only whispers until evidence is found. And now, the James Webb Space Telescope has turned those whispers into revelations. Webb has peered into the very edge of time itself, into the universe's earliest moments, and discovered something no one was prepared to see. In the depths of cosmic history, it found galaxies so ancient, so luminous, and so chemically evolved that they challenge not just our theories of galaxy formation, but the very narrative of the universe itself. This isn't just about isolated objects scattered across the heavens. It's about what they represent, evidence that the early universe's first billion years were not a quiet beginning, but a cosmic frenzy of creation, order, and complexity. What we once thought of as a long, slow dawn may instead have been an explosive sunrise, with galaxies burning brightly almost as soon as they could exist. Back in 2016, Hubble Space Telescope made headlines when it detected GNZ11, the most distant galaxy ever seen at the time. Its light had traveled for over 13.4 billion years, giving us a rare glimpse into an era when the universe was less than 400 million years old. For years, GNZ11 stood as a kind of frontier marker, a lonely beacon from the earliest known epoch. But Hubble, as powerful as it was, had limitations. Its smaller mirror and inability to see as deeply into the infrared spectrum meant that many of the faintest, earliest galaxies were simply invisible to it. Then came Webb, launched in late 2021 and stationed nearly a million miles from Earth at the L2 point. With its massive 6.5-meter gold-coated mirror and cutting-edge infrared detectors, Webb was purpose-built for a mission no telescope before it could truly achieve: to capture the stretched-out light of the universe's very first stars and galaxies. Almost immediately, it began breaking records. One of its earliest finds was JADE's GSZ-10, with a redshift of 14.32, meaning Webb was looking back to a time just 280 million years after the Big Bang. That alone was revolutionary. And then came something stranger still. A galaxy now known as MOMS 14, with an even higher redshift of 14.44. For cosmologists, this was jaw-dropping. We were suddenly staring into an epoch that seemed impossibly close to the Big Bang itself. But numbers on paper were only part of the story. MOMS 14 itself defied every expectation. At just 500 light-years across, it was tiny compared to mature galaxies like the Milky Way, which stretches over 100,000 light-years. Yet despite its small size, it was radiating like a cosmic lighthouse, blazing with intense star formation. By all accounts, it should have been faint and struggling to form stars, but instead, it was already a powerhouse of creation, birthing new suns at a rate galaxies of that age were never supposed to reach. When Webb's instrument split the light from MOMS 14 into a spectrum, the surprises multiplied. Embedded in that spectrum was the chemical fingerprint of nitrogen, far more of it than astronomers expected to see in such a young galaxy. Nitrogen doesn't just appear out of nowhere. It is forged in the hearts of massive stars, released into space only when those stars die in violent supernova explosions. Finding such high levels of nitrogen meant that multiple generations of stars had already lived, died, and recycled their elements into this galaxy, long before MOMS 14 was even born. This was a revelation. It meant that the universe had been producing stars and enriching itself with heavy elements much earlier than our models ever predicted. The cosmic dawn was not simply hydrogen and helium clouds slowly condensing, it was already filled with the ashes of stars, evidence of cycles of birth and death that began almost immediately after the Big Bang. Webb was showing us not just young galaxies, but galaxies with hidden ancestral histories buried in their chemistry. But the story deepened further. Typically, galaxies experiencing such extreme star formation are powered, in part, by the presence of a supermassive black hole at their centers. These central giants act as engines, regulating star birth through their immense gravity and radiation. Yet Webb detected no signs of a black hole within MOMS 14. No X-ray emissions. No energetic radiation from an accretion disk. Nothing. The galaxy was somehow running at full capacity without the very mechanism we believed was essential for such intensity. This directly challenges one of the pillars of modern astrophysics, the idea that galaxies and their central black holes grow together, each feeding the other in a delicate balance. If MOMS 14 can thrive without one, perhaps black holes are not as central to early galaxy evolution as we thought. Or perhaps we are catching this galaxy in a rare and fleeting moment, a snapshot before a black hole emerged at its heart. At first, astronomers considered MOMS 14 to be an anomaly, an outlier in an otherwise slow and quiet early cosmos. But as Webb's deep field surveys expanded, a pattern emerged. Dozens of similar galaxies began to appear, small, compact, chemically rich, and blindingly bright. Each one undermined another assumption, each one pushed the timeline of cosmic evolution further back. Some galaxies were even richer in heavy elements than MOMS 14, hinting at star formation and death cycles stretching further into the past than the Big Bang models allowed. Suddenly, what we thought of as cosmic infancy looked more like cosmic adolescence. The universe wasn't slowly stumbling toward complexity, it was sprinting. This revelation forces cosmologists to revisit their simulations of early galaxy growth. Star formation rates must have been higher. Chemical enrichment must have happened faster. And perhaps there were entire phases of cosmic evolution we have never even modeled. And then came another anomaly, rotation. When astronomers studied galactic spins across Webb's data and other surveys, they noticed something deeply puzzling. Most galaxies appeared to rotate in the same direction. In a universe governed by randomness, spins should be distributed evenly, half clockwise, half counterclockwise. Instead, the data hinted at a strange coherence, as if galaxies across vast distances were somehow aligned. This challenges one of the most fundamental principles of cosmology: isotropy, the idea that the universe has no preferred direction. If this alignment is real, it suggests a hidden order, a kind of cosmic architecture that stretches across billions of light years. Could the earliest galaxies, enriched with heavy elements and forming stars at impossible rates, be part of this grander design? If so, what forces were shaping it? Some scientists are now revisiting radical ideas long dismissed as speculation. One is that our entire universe might exist inside a black hole. In this model, the Big Bang was not the beginning but a bounce, a rebirth following the collapse of matter in another universe. Each black hole could birth a new cosmos with its own physical laws, and only universes stable enough to evolve survive. This would not only explain the fine-tuning of our universe for stars and life but could also account for the surprising organization we're seeing in the earliest structures. And then comes perhaps the most unsettling interpretation. What if the universe isn't just evolving, but self-organizing, aware, in some fundamental way, of its own growth? The improbable symmetry in galactic spins, the rapid chemical enrichment, the coordinated structures. These may not be random accidents but the fingerprints of a system that functions like a living organism. In this view, every star, every galaxy, and even every conscious being is part of a vast feedback loop, the universe observing itself, adjusting, and becoming ever more complex. For decades, astronomers suspected the early cosmos was not the quiet, primitive place our models described. Now, Webb has confirmed those suspicions with undeniable evidence. Galaxies blazing too soon. Heavy elements existing too early. Cosmic rotations showing hidden order. Structures suggesting design on the grandest scale. And radical hints that our universe may be just one of many, born from the depths of another. What Webb is revealing is more than discovery, it is transformation. The universe is not just random dust and chaos. It is structured, dynamic, and perhaps participatory. And we, tiny observers orbiting a small star on a pale blue dot, are not outsiders to this story. We are embedded within it, part of the same unfolding complexity that Webb is uncovering at the edge of time. So, what do you think? Are these discoveries signs of a designed, evolving cosmos? Or are we still underestimating the raw chaotic power of nature? Let us know in the comments. And if you found this journey into the oldest light of the universe as mind-shattering as we did, hit like, subscribe, and stay with us here at Discovery at 2.0 for more deep space revelations. Because the universe is finally revealing its secrets, and the truth is far more extraordinary than we ever dared to imagine.